All right, we're looking at a L'Hopital's rule question here. It's a little more challenging. You've got the function to another function power, and this gives you some different kinds of indeterminate forms, like infinity to the zero or 1 to the infinity, and those are indeterminate forms. Some people have trouble understanding like where those are coming from. I'll just give a little bit on that first here. So with something like infinity to the zero, you're looking at a really number that's approaching infinity as a base. And if you picture a really large number, right, 9999999 as your base, and then remember it's not just zero though. You might be like, well, anything to the zero power is 1, right? But remember it's a limit. So like the base is approaching infinity, but the power is approaching zero. And let's suppose that it's approaching zero from the right, for instance. Then you're talking about like 0.000001 maybe for like at any point in time, right? Like at any point for x, if this is the base at that x value, then maybe that exponent is maybe it's 0.0001, right? So now you're talking about the well, that's like 1 over what is that? 1 over 100,000. So now you're talking about the 100,000th root of 9999999, right? And I don't know. I could get out a calculator, but you could imagine how if this number is really, 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 really big compared to this number, perhaps this value will actually be quite large. But if this value is really, really big, this index, or if this is really, really small, in other words, compared to this number, then the root could actually make it get really close to, maybe 1, right? And then if it's approaching 0 from the other side, the negative side, that just puts the whole thing over 1. So you can actually have values on the other side of 1 as well. And you could go all the way down towards 0 that you're approaching. And so the point is there's a lot of different possibilities, and it depends, again, on which, like how quickly that base is growing compared to how quickly that exponent is approaching 0. And it's the same idea here. Again, you might be thinking 1 to any power is 1, but remember, it's not 1. We're talking about limits. And when you're talking about a limit, we're not talking about 1. We're talking about values near 1, right? So if you have a value that's very close to 1 for your base, like 1.0001, and then you have a very large power. If the power is large enough, it might make that base grow really, really large. If we're really close to 1 and the power is not quite big enough to outweigh how close to 1 the base is, maybe we'll just be really close to 1. And if we're at like 0.999 on the other side of 1 for the base, right, and to a large power, something approaching infinity, laughing at my pathetic infinity there. Again, it depends. How quick is this getting close to 1? How quickly is this growing? It could go all the way down towards 0. It could go up toward 1. So depending on which side of 1 we're on, depending on how fast that power is growing, again, indeterminate form really could end up being anything. So that's what we have here. In fact, this is the infinity to the 0 power scenario. So you can kind of, if you need to, write that down over here, like infinity, plus infinity, plus a lesser infinity, right? X is not as powerful as e to the x. And then to the 1 over infinity, well, it's like the 0th power, right? And so that's this scenario. It is an indeterminate form. So again, we're not saying it equals that. You never want to write that because this is not a number. This is not defined. And this limit very well might exist. All right, how do you handle it then? It's not in a form that we can do L'Hopital's rule right away. So what we need to do is separate the power from the base. And the way we do that, just like if we wanted to do a derivative on something like this, is we're going to introduce a natural log. And you might think, hey, this is complicated. What do I want to do to something that's already complicated? And I don't know about you, but I'd say let's just throw in a logarithm, right? Why not? If you think that's crazy, keep in mind by taking a log on the right side, it lets you use the properties of logarithms and bring that power right down there. Separate the power from the base. That's what it does. So I kind of just set y equal to the inside of this. To be formal, I should say let y equal. And then maybe in another step, so the natural log of y equals the natural log of this, right? And maybe I'll rewrite that in a minute just to make it more formal. And so then the natural log of y equals 1 over x times the natural log of e to the x plus x. And we're taking what we ultimately want is the limit as x approaches infinity of y, right? What we're going to do is find the limit as x approaches infinity of the natural log of y, and then we're just going to exponentiate, and that'll give us the limit of y at the end. So again, like a formal step here would be let y equal this, e to the x plus x to the 1 over x, and then we're taking the natural log of both sides and just doing a little work here. And hey, I could rewrite that as the natural log of e to the x plus x over x. And now I have this fraction. And now when I plug in, infinity, I'm going to get infinity over infinity. Now I have a L'Hopital's rule situation. That's the approach we're going to take here. We're going to take the limit of both sides as x goes to infinity, because if we do that, then we're getting the limit of the natural log of y as x goes to infinity. And what we want at the end is the limit of y as x goes to infinity. So all we'll have to do is exponentiate that, and we'll have our answer. So let's start with the limit as x goes to infinity of this fraction right here, the natural log of e to the x plus x divided by x. And again, you want to show that you can use L'Hopital's rule. Anytime you use L'Hopital's rule, show that you can use it by showing that indeterminate form 0 over 0 or plus or minus infinity over plus or minus infinity. In this case, you can tell it's going to be infinity over infinity. So all you got to do is show it this way. The natural log of e to the x plus x. I guess I didn't really need that extra parentheses, but that's okay. That's infinity clearly, right? E to the x goes to infinity, x goes to infinity. They both, together go to infinity. The natural log of something growing infinitely large is also infinitely large. It just grows really slowly, right? Natural logs do. But the exponential grows really fast, and it, kind of counteracts that. It actually exactly counteracts that, right? They're inverses. And the limit as x goes to infinity of x, the denominator, is also clearly infinity. And so since it's an infinity over infinity form, that is one of the forms that allows you to use L'Hopital's rule. And so we can say this limit equals, by L'Hopital's rule, the limit as x approaches infinity of, and now we're going to use the derivative on the top and bottom, right? The limit of the derivative of the numerator over the derivative of the denominator. The denominator is easy enough. That's just 1. The numerator is not so bad. It's 1 over the inside, right? And I'm writing it this way, even though we can kind of, maybe you can skip the next step here, but it's 1 times the derivative of the inside, right? Like u prime over u is the derivative of natural log of u. And so that's just going to be e to the x plus 1. Again, this is one of those scenarios where I say this in all of these. When you're doing L'Hopital's rule, don't like anything you can do on limits, any simplifications you can do, you can still do them. So absolutely simplify this. And so what we'll get is, I'll just kind of keep going in line here. The e to the x plus 1, the u prime part, will stay on top. And then this like over u part, that e to the x plus x, we'll just put it in the denominator of this bigger fraction. And now we're good to go. So, careful though. What I've written there is incorrect, right? I was simplifying the inside of this limit, but it's still inside of a limit. So you just kind of, boards grouped this all together. So let me just squeeze a limit in there. It's not correct to take the limit out of there because we haven't evaluated the limit yet. And again, we still have an infinity over infinity scenario, right? So we're going to go ahead and do this again. We're going to do L'Hopital's rule again. The limit of e to the x plus 1 as x goes to infinity is infinity. The limit as x goes to infinity of e to the x plus x is also infinity, which means we can use L'Hopital's rule again. And if you're thinking, well, I don't know, is this going to go anywhere? If you're not sure, maybe it is, maybe it isn't. Maybe you already know. Maybe you already know this limit just by kind of giving it the smell test, right? Saying, hey, the dominant thing on top is the e to the x. The one is piddly and insignificant by comparison. The dominant thing on the bottom is e to the x. The x is piddly and insignificant by comparison. I think that's legit. You can do that. I allow that. Pretty sure that flies on the AP exam as well. And so you could say, it's really just boils down to e to the x over e to the x as x approaches infinity, which is 1. And that is what this limit will end up being, this limit, not the whole problem, but this limit. But, if you want to show it with L'Hopital's rule, since that's what we're learning right now, I'm going to go ahead and do it. Oh, by the way, I never wrote by L'Hopital's rule here, so let me do that. And I'll do it again on this next step too. And so again, equals, and now I'm going from here and I'm using L'Hopital's rule again, the limit as x approaches infinity of, on top we just get e to the x, on the bottom we get e to the x plus 1. And this, I'm not going to do it again at this point, because I feel like if we didn't see it here, which we talked about it, we did, clearly we can see here that plus 1 doesn't really matter, right? Anyway, this was also by L'Hopital's rule. And if you wanted to prove it again with L'Hopital's rule, it would just take one more time, because one more time that plus 1 goes away, and then you have e to the x over e to the x, which is clearly 1. But this limit is clearly 1, I think. Like you have to be able to see that, as x gets very large, these numbers get huge, and then the plus 1 does almost nothing. And so it'll basically be 1. It's approaching 1 from the left, right? And maybe that's useful to make a note of. Here, I'll just say from below, from the left, because that denominator is just slightly larger. Okay? So that's not done though, right? The limit of this is 1, but that's not what we were asked for. What we just found was the limit of this, which is the limit of the natural log of y. We still need to exponentiate. So here's what I'm going to say. I'm going to say and maybe I should do this down at the bottom, but I'll do it up here. The limit as x approaches infinity of the natural log of y is 1. And so the limit as x approaches infinity of y, well, you can just you can compose these functions. You can exponentiate both sides of this equation and pull the natural log out of the limit and take the natural log of the limit of y. And then the e to the and the natural log of, they cancel each other out. And you end up with just, y equals, and on the other side you get e to the 1. And so that's just e. And that's what we want. This limit is e. That's our answer. Okay. And, my work here isn't very linear because I'm kind of going back up there. So I'll take this and I'm going to put a little arrow up here. And maybe I should have, like I said, written it at the bottom. And then this is the actual answer that we want. So good. That's it. You can do that with logs, with limits, with logs that are inside of limits. You can pull them out of the limit. With exponentials, same thing. And that's how you attack these problems and solve them.